Hello, I'm Richard Stanley, and I wanted to share a project that I've been working on around how to see transmitters that are really, really nearby, like in my dining room nearby, and how to kind of visualize those in a heat map to show angle of arrival and to show magnitude. So there's so many things on YouTube that are awesome that get into radio stuff, and this is one that I found pretty inspiring, which is a presentation by Natasha Hurley Walker, who is a radio astronomer in Western Australia. And the folks there have an enormous array of dipoles in the desert, and they're able to create these kind of, post processing, of course, but they're able to create these kind of amazing radio views of the Milky Way. And so just to kind of learn the basics, reinvent the wheel in order to learn, I wanted to build something that could detect very simple things in a very confined environment. And so I wanted to use GNU Radio and to use some SDRs. And again, this is a work in progress, so there'll be issues that we'll discuss. First thing I'd like to show you is a simulation. This is a 2D simulation. All the simulations and everything are available in my GitHub. And the hardware tests as well. So in this simulation, what's happening is that I'm moving around a transmitter, kind of a pseudo transmitter, simulated transmitter, with regard to its phase, in both azimuth and elevation. And the top thing is elevation, next is azimuth in these Qt GUI time raster sinks. And on the left is a video SDL sync, which combines those. So what this shows is that as you move the transmitter around, you should be able to visualize that in the time raster sinks, but also together in the video SDL sync. And this is the goal, right? So this is how I kind of tried to figure out the math and how to do it in GNU Radio. Okay, so how this is working under the hood is that let's say a radio signal hits one antenna before it hits another. Those are separate radios, and therefore, if you lag a signal with regard to the other, you should be able to see the energy in that direction, right? And same as the other way. So you lag one signal with regard to another, you should be able to see the energy. So you lag, and then you combine those signals, and then you can create an array of pixels in which the brightness or the darkness represents energy, and you have it for each of those kind of steering vectors or weight vectors. In GNU Radio, it looks like this. You take signals from and this is a one-dimension example, right? So it's just two radios. So you take signals from the left RX and the right, left and right, so like an azimuth, and then you lag their phase, and then add them together and take the magnitude. Okay, excuse me. Only the best. So Legos for holding the antennas, eBay log periodic dipoles, and actually great radios. So these are Edis user B210s, and these are phase coherent within themselves, right? So there's two receive, two transmit on these. I'm not using the transmit, but so there's two receive. So in one B210, they're phase coherent, which means you can resolve the differences at a pretty small, number of radians or degrees between signals. And there's one for each dimension. And then there's a ham HT used for the transmitter. There's a couple of mini circuits attenuators on there. I already blew up one daughter board accidentally in doing this, so pay attention to link budgets. All right, so I'll do a demo. This is a one-dimensional demo. So this is just one B210 and two antennas. All right, so as I move the radio around, you should see that there is some tracking of it in terms of direction of arrival as well as magnitude. So the brightness or color, it depends on which view you're looking at, represents the magnitude, and then angle of arrivals being represented by the by where that's moving. So that's one dimension. That's pretty straightforward and a lot of fun, actually. All right. So now I'll get into the work in progress. This is the two-dimension example. This is a little more complex, and I'll explain why. Mostly not because of the math as much as my limitations of my antennas. So as you kind of move the transmitter around an axis in which the polarization is lined up between the receiver and the transmitter, no problem. So if you're like this with elevation, like this, with azimuth, no problem. But when you get in the corners in these quadrants, like it breaks down. So it sort of works, but I think this requires some new antennas. So if anyone knows how to get circularly polarized 70 centimeter antennas that'll fit in my dining room, that would be great. And I think that will kind of solve that issue. Okay, so that's about it. Thank you for attending. And if you want more about, like, listen to a real expert about phase arrays and beamforming, John Kraft, the Analog Devices, is running a workshop on Thursday. Look forward to that. That's going to be great. And also, there's some fun stuff in GNU Radio 3.9, which is coming out in coming months, and that has a lot of fun stuff. Thanks to Mike Piscopo. And if like me, you're having fun with this and you want to enjoy some YouTube videos, GRCon 2017 is just so amazing for this. They're fantastic presentations by Travis Collins and Sam Whiting and Ben McCall and Will Myrick. So please check those out. Those are just great fun for DOA and beamforming stuff. Again, I'm going to put all the flow graphs and demo stuff and all that kind of stuff in the GitHub repo, citizenrich/seeing signals. Thank you, and have a great conference, and be safe.